Hey, recording is rolling. It is Wednesday, October 2nd. There's a one question for you guys. So there's an incline Atwood looking setup. I also threw in a coefficient of friction here. After that, you guys should have a quarter page on your desk and some spring scales. We'll do a Hooke's Law lab activity later. And I'll see how much time we have left over. Possibly give you guys time for some textbook puzzles, answering questions you guys have. Yeah, I do have some polyfield demos that's planning to show my other classes, so possibly roll some of those if you guys want. All right, but here, let's focus on this incline Atwood right here. Here, I'll walk you guys through it step by step. Right, these are going to be multi-step complex processes. Right, so you guys see that right there. Here, I'll draw it as you guys draw it. We'll all draw it together. Here, two. All right. All right, so here, now this one's a really steep angle. I've got 53.1 degrees on there. So now you do have a protractor on your desk. If you want to measure that out, you could, but I'm just going to eyeball it and say it's probably pretty close to that. Just pretty steep. I mean, it's more than 45 degrees, right? 45 degrees would be like an isosceles right triangle. So, right. So 53 degrees is getting pretty up there. Put a little pulley up here at the top. Okay. And I got a couple of masses. So, yep. Oh, no. This is for your notes. Yeah, all right. Guys, the quarter page we're going to save for later. Yeah. All right. Let's see, we're one of those like size 0.5 artists, 0.5 font artists. But no. Right. Yeah, so this is just for your notes. I think I may have mentioned yesterday, but when I eventually get you guys your quiz, that there is a quiz question that looks kind of like this. It's not exactly the same ask, a little bit different, but this will definitely help you out. All right, so you guys are drawing that. Ooh. Here we go. I think that's better. All right, got a couple of blocks connected by a string. Like that. All right, I gave you guys this angle, 53.1 degrees, right, which that should look like a familiar angle. Guys, why am I giving you that angle? I'm setting up a what geometry? 3, 4, 5 right triangle geometry, right? 3, 4, 5. Right. What else you got? I gave you a couple of masses. I gave you guys this is a mass of 1 kilogram over here. I gave you guys this is a mass of 2 kilograms over here. Right, the one same. All right. And then one last detail, as I said, there's a coefficient of friction between these two surfaces, between this block and this steep surface. I said the coefficient of kinetic friction, I guess it's going to be sliding. Let's call it 0.333. Okay. Okay. There you go. All right, so I just took that picture, just copied it while you guys are drawing it. All right, so now we all got that. Right now, before I kicking off this process, it's good to step back, get a force for the trees, picture what's going on, think of maybe related questions you could ask. Okay? Do you guys see? I call this guy 2 kilograms, this guy 1 kilogram. Right now, I'm trying to make it really obvious which way this is going to accelerate. Guys, is this going to go counterclockwise or clockwise? Clockwise for sure, right? Right. Now, the fact that there's some angle here, because what if this was a shallower angle? What if it said 53 degrees? What if it was like 40 degrees? And just you can play around with this angle, right? Imagine like an animation, you can play around with that. Well, what if you change these respective masses? Right? Like what if instead of 2 kilograms, what if it's 1 kilogram? Right, it's probably still going to go clockwise, maybe. Although maybe now there'd be enough friction that it would just stop it at that point. It wouldn't go at all, right? Guys, what if this is like a half a kilogram? Do you think maybe actually this would possibly switch and go the other way, right? Maybe that could be a good question too. Is I wonder at what point maybe make this mass smaller, smaller, smaller. At what point does it stop moving? And then if you make it too small, at what point does it actually start to move the other way? Right, those could be good questions, right? But usually, a good thing to do is to make a pretty good guess as to which way it's going to go. You guys said clockwise. Yeah, I think that makes sense to go clockwise. Right? And that is going to be important specifically for the direction of friction. Like if this was a frictionless surface, it wouldn't matter. You could just go into a blind and you get whatever answer, right? But guys, the fact that there's friction, whichever way this block is trying to slide, it doesn't friction always point the opposite way, right? That's why it's important to make a good guess as to which way this is going to move to start with. So guys, good so far. Good so far. let's get some forces free body diagram type. All right, so you guys think this 2 kilogram mass here, should just hang it down here. How much weight is this right here? 20 Newton. Yeah, let's go ahead and call it 20 Newtons. Okay. So okay, I'll just label it 20 Newtons. Okay. If it was a free response question and it was really open-ended, maybe call it like mg or something like that. But I'll throw 20 Newtons. We know that. Okay. How much does this guy right here weigh? 10 Newtons. Okay. And if you draw everything to scale, should that be about half the length? Right. Like because 10 Newtons is half of 20 Newtons. Right. I'll try to get pretty close. So that'd be a 10 Newton force right there. Bam, 10 Newtons. Okay. All right. How about let's do tension. Do you guys think there's a tension in the string? Right. Do you guys think that tension is probably going to be between what and what? Do you think? Probably somewhere between 10 and 20. Right. I'm gonna make a guess, probably about 15. That's probably not exactly the answer, but it's probably pretty close to that. So I'm gonna try to draw it so it's kind of close to that. Right. All right. Yeah. So it's the same tension for both. I'll call it F sub T for tension force. Okay. Maybe that could be an extension question. We'll go back and figure out what the tension is later on. Right. But first, we got to figure out what's the acceleration. We're gonna do a whole systems approach, like I prefer to do myself. Okay. There is one more force you needed on this. Guys, which force am I leaving off? Oh, whoops. Sorry, two more forces. Okay, normal force and then friction, right? Okay. Yeah, so let's definitely get normal force. Can you guys hold your ruler perpendicular to the surface? Notice perpendicular to the surface. Okay. And draw, oops. Okay, got my mouse number in the way. That's all right. Get that. Okay. And say how long should that actually be? Well, maybe actually before I drew that normal force, I should have broken the weight into components, maybe, right? It's probably good to do at some point. Okay? I like this triangle method myself. That's what I've been showing you guys, this triangle method. You guys see, here, I was holding my ruler perpendicular to the surface, and now it's going to be parallel to the surface. You guys see parallel to the surface? Okay? Guys, am I holding it parallel to the ground? No, it's parallel to the surface. Okay? And then dash this off. Maybe it's more obvious if the angle is really steep like this. Right? Like this. Some textbooks, some teachers might do a parallelogram method. They might do like put it over here and do like here. I'll draw a full like parallelogram, right? Real light, maybe something like that. But okay, just focus on part of that. Maybe it looks like a triangle. Oh, okay. Now, guys, what angle is this right here? 53.1 degrees. Aha. Okay. And let's see. How about this? How about this right here? What is this component? And notice I dashed it. You guys did dash it, right? You guys didn't make it solid. Dash it. Okay. This is equal to what times what? Yeah, 10 Newtons times what's adjacent? Cosine at 53 degrees? Yeah. So I'll label it 10 Newtons times cosine of 53.1 degrees. Okay. And cosine of 53.1 degrees, maybe you guys know that. There's a reason I picked that angle. Ooh, this got bumped again. All right. So my audio is weird there. Guys, what is cosine of 53.1 degrees? Yeah. Okay, there you go. So this is 3/5, and then times 10 Newtons. That should give you 6 Newtons. So equal to 6 Newtons. Right. Right. Now, I was kind of imagining that before. Okay, while I was drawing this normal force. Guess this normal force exactly cancels that out. Right. So now we know what the normal force is exactly equal to. How much is the normal force equal to? It's got to also be equal to 6 Newtons to balance out the 6 Newtons right here. Picture. Right. How about this component right here? What's this? Yeah, there you go. 10 Newtons times sine of 53.1 degrees. Sine of 53.1 degrees, is that like 4/5? What's 4/5 of 10? 8 Newtons. There you go. Got it. 8 Newton, well, component of the weight that's trying to move the whole system counterclockwise. Right. Okay. So now I still need what force you guys just said? Friction. Right. Now you guys were saying this is going to be clockwise. I think that makes sense. So which way do you draw the friction force? Yeah, counterclockwise. Okay. Now if I draw it to scale exactly, I gave you guys this coefficient of friction of like 1/3, 0.333. We can call that 1/3, right? Okay. So should that be 1/3? 1/3 of what? The what force? Normal force. Normal force. You guys remember? Here, I'll write this in the corner here. You guys remember? Friction force is equal to coefficient of friction times the normal force. You guys remember that? Right. So now that this normal force is already established, in fact, we know it's 6 newtons. Right, that's 6 newtons right there. Guys, what's 1/3 of 6 newtons? 2 newtons. Okay. Let me try to draw it kind of scale. I guess it'd be kind of a small looking force. So friction force must be equal to 2 newtons because friction force equals 1/3 of 6 newtons, which is 2 newtons. Friction force is 2 newtons. All right. All right, I think we got all the force and force components that we need to move on to the next step. Like I said. Right. So I'm going to write out this phrase that I've seen AP write, which is a whole system approach. Okay. This is in contrast to the other way to approach this would be to do this block in isolation, make some equations, this block in isolation, make an equation, and then do a system of equations. Okay, which, okay. But I'm going to do this whole system approach. I'm going to look at this as one giant system that's all tied together. And if I do that, then would this tension force be internal or external to the 2-block system? Just internal. It's just holding the blocks together. Okay. So from using this approach, I can ignore that for now. Maybe I can revisit that question later, but I'm going to ignore it for now. I'm going to say I really care about 3 either forces or force components. Let me switch ink color here so I can maybe circle these. Okay. This 20 Newton weight, that matters, right? Right. That's driving the system in the direction you guys said it was going to go. So I'm going to circle that one because that one matters. Okay. Right. Okay. Now over here, I know we have a whole mess of stuff going on, right? But there's really only a few components we care about. Remember, this tension is just internal with this tension. So okay, so I'm going to ignore that. Guys, do you think this normal force is driving the motion? Not by itself, although it's related to the friction force, which does matter, right? That this friction force is trying to hold everything back. So I think that one's going to matter. Okay. And also, what other one do I have to circle? Not the full weight, but what? The sign component of the weight, which is just the 8 newtons, not the full 10 Newton weight, but just the 8 newtons component that's trying to pull it counterclockwise. All right, guys, yet? Okay. If you want extra practice with this, of course, you guys know there's a few in the solutions manual we were looking through yesterday that looked kind of like this. Yeah. Okay, guys, it's not the full 10 newtons that's pulling down. Maybe it would if it was just like a double elevator. But the fact that it's on some inclined surface, only the 8 newtons actually pulls it in along the surface in that direction. Only that. Maybe if I change this from 53 degrees to like 45 or 37, maybe it make more, maybe be more obvious why it'd be that. Right? In fact, if you took those 53 degrees all the way to 0 degrees, turn it to just the modified output like you guys did in the lab the other day, then there wouldn't be any component of its weight at all. This would shrink all the way to 0, right? And now this block would have inertia. It'd be slowing it down for that reason, but there wouldn't actually be any component of the weight that would be causing that. Right? Guys good? Right. So let's do Newton's second law of motion here. Can you guys do acceleration is net force on total mass? Right? Okay. Okay. I could squeeze it in that margin, but it'd be really tiny. So here, I'm going to use more paper. Okay. Is that okay? Use more paper here. So acceleration is net force on total mass. Acceleration is, all right. So net force, what should I write for net force? This 20 clockwise minus the 8 and 2 pulling counterclockwise. Is that true? Okay. So I'll do 20 newtons says let's go clockwise minus the 8 newtons and 2 newtons saying let's go counterclockwise. That would be the net force, wouldn't it? Or you do 20 minus 8 minus 2. That's okay too. Distribute that negative. That's all right. Okay. Is that right? Yeah. Okay, because it's like two guys playing tug of war, right? Tug of war. Suppose you're playing tug of war over a pulley. This guy's pulling with 20 newtons. This guy, well, it's really two forces that are trying to resist that, right? We've got this component of the weight that's 8 newtons saying, no, let's go counterclockwise. But don't forget also this friction force is further resisting that motion. So these two are acting sort of like in conjunction with each other, trying to pull it back the other way. Yeah. Yeah, why not use the full 10 Newton weight? Because not all the weight is pulling parallel to that surface. Only 8 newtons is, right? Which is most of the weight, but it's not actually all. Like here, what if we do an animation? Like what if we do a really steep curve and then kind of a middle curve incline and then a pretty flat incline, right? And then what if here, just for completion, what if I do a flat tabletop, right? Put a little pulley up here. Okay. If you can imagine this animation in your mind, let's just focus on the block that's on the surface. I think what's going on with those forces. Okay. So we got here, let's switch to pink ink to make this more obvious. Okay. All right, so I got this weight here. Maybe it's the same weight block over and over and over. Same weight block, right? That'd be true. Right. And then here could be the normal force with this would be pretty small. This normal force is kind of medium. This normal force is getting pretty big. It's almost equal to the weight, but it's a tiny bit shorter. This normal force is exactly equal to the weight. Okay. mg, it's the same mg. Okay, I don't know if I drew that 100% to scale, but it's pretty close. I got a little tiny normal force there, and kind of a medium normal force there. Normal force getting almost equal to the weight, and here the normal force is equal to the weight. Okay, something like that. Okay. Now if I break this weight into component, well, okay, my mg is kind of in the way. Oops, I didn't mean to do that. It's okay if I break it into components the other way, kind of go parallel first and then perpendicular. It's the same. It gets you the same result when it's okay. So, sorry, it's a little bit backwards, but okay. Stretch your guys' imagination a little bit. Okay, but get the same result. I can still make the same point. Okay, which is right, and then this one doesn't need any components at all. Right, right, so the example we're in the middle of doing is a really steep incline. So this component that's actually pulling down to the left is almost equal to the weight, but it's a tiny bit less. Right? Then if you make the incline shallower, it's not being pulled down as much. Right? Now, you guys' car and incline lab, one of the first big labs you guys did, was a pretty shallow slope. It was like, what, 5 degrees or something? Right? So yeah, there was a tiny component of the weight that was pulling along. Right? You could just do mg times sine of that angle is what it works out to be. Sine of 5 degrees is real tiny, right? And then if you went straight horizontal, well, now there's no component of the weight that's pulling it left at all. Yeah, so it shrinks down. Okay, so you guys see that? All right. So back to here then. All right, so we got this. I got 20 newtons saying let's go clockwise. We got the 2 and the 8 in conjunction pulling back counterclockwise. Okay, and how much mass is being moved? 2 plus 1, right? 2 plus 1. So got 2 kilograms and also another kilogram. Right? Would that be true? Good. Right. So the acceleration is, let's say I got, looks like a 10 Newton net force acting on 3 kilograms mass. Could that be, what, 3.3 meters per second squared? Think like that. I know in the AP exam, if this was a multiple choice question, a lot of times they like to round to like 2 digits like that. So that'd probably be exactly the answer they would offer. All right. All right, guys, good. All right. You guys want to go hit that follow-up question? What is the tension in the string? You guys remember that tension in the string? Now, before we start, I was saying I'm going to guess it's probably about 15 newtons. That might not be exactly right. Let's see what exactly it is. Now, there's 2 ways you can get the tension in the string. You can either focus on this block or focus on this block. Now, guys, which block do you think is probably easier to focus on to get to the answer? Yeah, probably one was just hanging because it's just got 1, 2 forces on it, right? Either way you do it, you got the same answer. Let's just focus on that one. So the one that's hanging straight down, it's got a 20 Newton weight. It's got some mystery tension force that I know is less than the weight in magnitude, but I don't know exactly what it is yet. We got, of course, 2 kilograms mass. Should that black ink on. Okay. 2 kilograms mass. Okay. All right. So let's go back to Newton's second law of motion. Here, I'll write it in the non-fraction form. F equals ma. Okay. Now this net force is, or no, that's really generic. That's like straight off the poster, straight out of a textbook. Okay. Now for this particular application, for this vertical hanging block, what do I write for the net force? 20 newtons minus the tension force, right? This down minus this up gives you the net force. That'd be true. Let's get with this. Get that later. All right, is that okay? And we're honed in on the 2 kilogram block, 2 kilograms. And it's accelerating how much? Aha, yeah, 3.33 meters per second squared. We got that before. Well, if I saved an extra digit, I could throw another 3 in there, right? 3.33. Is it 10/3 meters per second squared as a fraction? Maybe I'll just do it that way, 10/3 meters per second squared. Okay, just like that. All right, so if I rearrange this a little bit, I can get tension force. This is just an algebra step. Add that, subtract that, equals 20 newtons minus, see, 2 kilograms times 10. So it's 2 times 10 is 20 over 3 kilogram meter per second squared is newtons. So I guess it's something like that, right? Swap. Plus 20 minus 20 over 3. That is, aha, tension force is 13.3, and that would be newtons. Yeah. Okay, so remember from the outset, I was guessing that's probably kind of close to 15 newtons, probably-ish. Right? Yeah, that's pretty close right there. All right, guys good there? All right. Yeah, and again, there's so many variations of it. I took you guys through a pretty straightforward one, right? But like I was saying at the beginning, you could play around with variables and ask so many different questions, like what mass would this have to shrink down to cause either constant velocity or for it to stop, or how small would that have to be to reverse it? Right? Oh, what I think one of the textbook questions goes like, if you know what the acceleration is, can you solve for the necessary coefficient of friction to make that happen? Right? That'd be a fun variation. I guess if you want to be really tricky, you could solve for like what angle could put it into equilibrium. Okay, there's so many ways you could go with that. All right, guys, set so far. You guys good? All right, so you guys have a quarter page on your desk. You guys got some spring scales. Well, got some spring scales up here. So you got the. All right. So yeah, there was a lab activity I've been wanting to do, and I think we have some time to fit this in right here. Give you guys some lab points for this. Guys, write your name on the paper on the quarter page. You guys got your name? All right. This is going to be spring constant lab. Okay. All right, guys wrote your name. You guys wrote spring constant lab. All right. How do you guys turn this? Yeah. Okay. We got plenty of time. I think we're going to be good. I want you guys to figure out what's the spring constant in each of these springs. Okay, so I think you have 6 spring scales on your desk. I have 5 of them up here. I just don't have the blue one. But here, let's do K. Guys, K is what does K stand for in physics? Spring constant, right? Lowercase k. Okay. So we'll do the blue one. We'll do K for the green one. We'll do K for the brown one. We'll do K for the. See, there's an order to these. I think it goes red, K white, and K gold. Okay. I say equals. Okay. Something like that. You think? All right, I'll get Zafar. Good. All right. Now, we're talking about which law is this? Whose law? Hooke's. Hooke's law. You guys remember Hooke's law right here? Hooke's law. Right. So see, F equals kx. Sometimes you see it F equals negative kx if you're talking about the restoring force, whatever. Right? So this spring constant, how stiff is this spring in the spring scale? Remember, that's there's some relationship between how much force you put on the spring and how much it stretches. Or if you had a compression spring, you could go that way too, but these are stretchy springs. Okay. So that ratio is Hooke's law. So let's try this out. If I need some space to do some math, maybe I could do some math back here. Yeah, I'll pick the brown one. The brown one is probably pretty universally useful, versatile, right? Okay, so the more force I put on, the more it stretches. Now, conveniently, it tells me what the force is, and I can measure how much I stretch it with a ruler. Okay, this one's a little bit broken, or maybe I'll start at the 20 and pull it from here. Okay, so let's see, maybe for example, to stretch it to 10 newtons, that takes, what is that? 5.3 centimeters, I think, 5.3 centimeters. Okay, so if I set up F equals KX, could you guys rearrange that and say K is equal to F over X? From the zero line, right? Because guys, if it's calibrated to 0, 0, zero force is at 0 stretch. Okay? X is how much you stretch it past its equilibrium point, right? So it starts out unstretched. Okay? Okay. Then you measure, oh, whoops, sorry, I want the newtons. Okay. So I got K, now this is for the Brown scale. To get to 10 newtons of force, I had to stretch it 5.3 centimeters. Right, just like that. So divide that out, see what I get. 10 divided by 5.3. Okay. That's K Brown equals 1.89 newtons per centimeter. It's one way to do it. Right. Now, more often, guys, what do you think is more common unit to see? Instead of Newton per centimeter, think Newton per meter. It's probably kind of common. Right. Let's put this in Newton per meter. Right. So I got 1.89 Newton per centimeter. Let's do a little dimensional analysis, a little unit conversion. Okay. Guys, how many centimeters in a meter? 100. Does the number 100 go on top or on bottom? Top. 100 centimeters, 1 meter. Could that be 189 newtons per meter? Or something like that? 189? Okay. All right. So I just solved this right here. I got 189 newtons per meter. Just like that. Okay. Oh, yeah. All right. All right. So you guys can follow Hooke's law. You have some force. There's some associated stretching distance. Just divide the two. Okay. Okay. And if you put it in newtons per meter, do you guys think all these spring scales is going to probably be a similar order of magnitude? So somewhere in, probably somewhere in the hundreds. Maybe for the green and blues, it might be less than 100. That's okay. Right. But should be kind of a similar order of magnitude, I think. Right. Newtons per meter. Okay. Okay. So go ahead. Solve for the spring constant for each of the spring scales. Turn that to the gray tray. I'll give you guys credit for that. And then, okay, so we got some time. So if we got some spare time, I can help you guys out with textbook puzzles. And I do have some Paul Hewitt videos I'm going to roll for my other classes. So I might roll a couple of those at the end of class too.